Good afternoon, everyone. My name is Hojung. I is working at the Korean Institute of Civil Engineering and Building Technologies as a senior researcher. First of all, this is a great honor to have opportunity to present my previous research and also my research, which is entitled Development of High-Value Bimetallic Catalysis from Metal-Contaminated Water. So this is content of my presentation today, so I'm going to start my talk with brief introduction. So, as you know, the rapid development of the semiconductor and secondary battery and display industry has led to increase the amount and concentration of metal-contaminated wastewater. As you know, this metal-contaminated wastewater is highly toxic to the human health, and also these metals are becoming increasingly valuable due to the resource depletion. As a result, metal resource recovery technologies such as adsorption, chemical precipitation, and membrane process, and also electrochemical process are gaining great attention. However, conventional process require additional post-chemical treatment to reuse metal ion, and it leading to a secondary environmental pollution. The adsorption process has a great advantage due to their strong ability to the diversity of coverage, simple operation and maintenance, and also reasonability. However, additional chemical treatment is required to recycle these metal ions, and recovered metal requires the post-processing to increase their purity, and the economic feasibility is quite questionable. So in this study, our strategy is the metal upcycling technology after absorption process to the upcycle as catalyst after metal adsorption without additional post-chemical treatment. As you know, there are lots of adsorption mechanisms including ion exchange, electron attraction, and hydrogen bonding. However, this adsorption mechanism is a low selectivity and thereby leading to low purity. So in this study, we applied a strong galvanic replace reaction, which is a driving force resulting from the difference in redox potential between metal and alumina. Alumina has a low redox potential, which is about minus 1.66 volt, which allows it to selectively absorb precious metal with a higher redox potential, such as gold and palladium and platinum and silver. So in this study, we developed copper and palladium bimetallic catalysis to utilize the gamma alumina to recover the catalysis from the metal-contaminated water, and we analyzed this and validated through the selective adsorption mechanism and catalytic reaction performances. So this is the material methods. We used two different phases of alumina, such as alpha alumina and gamma alumina, and we used 4 different metal ions and spiked into the DI water. And we did a batch experiment test and continuous column test, and also we evaluated the catalyst performance test. So this is the experiment condition of each experiment. So as you see the result, at a lower pH, the alumina shows surface become more positively charged and reducing adsorption efficiency. So in the pH 3, no adsorption was occurred, but the pH 5 and pH 7, there is a palladium and copper was observed on the alpha and gamma alumina. The larger difference in redox potential with alumina, with aluminum, the larger difference in redox potential with aluminum, the more effective galvanic replacement reaction occur, leading to the better adsorption on alumina. As you see the figure, gamma alumina exhibits a higher adsorption capacity than alpha alumina. At pH 7, alpha alumina carries a positively charged, while gamma alumina carries a negatively charged. However, gamma alumina has high specific surface area, which is approximately 400 times larger than that of alpha alumina. For alpha alumina, its low pore volume and high density cause channeling issue in the column. So as a result, adsorption does not occur efficiently in the column test. However, for the gamma alumina, similar to the batch test, adsorption occurs most predominantly in the order of the palladium, copper, nickel, and cobalt. At pH 7, most of palladium and copper were absorbed onto the gamma alumina. SEM images show that no adsorption occurred on the alpha alumina in the column test. while palladium and copper observed on the surface of gamma alumina. They also experienced results show that no changes in peak of alpha alumina before and after column test. For gamma alumina, after column test, peak appeared at the palladium and copper. And so we did absorption at the different pH. At pH 5, the absorption amount is lower than at pH 7 for palladium. As concentration in solution increased, the absorption amount slightly increased, while the copper, the difference is negligible. At pH 7, absorption to alumina occurs in proportion to the concentration ratio, palladium and copper in the solution. So we investigated the effect of hydrogen flow rate. So, and nitrogen selectivity is the highest at 77.5% when hydrogen gas flow rate is 10 ml per minute. The higher the hydrogen gas flow rate, the lower in the nitrogen selectivity. Therefore, adequate supply of hydrogen ion promotes the conversion to the ammonia, which require more hydrogen for the reduction. After that, we investigate the effect of palladium and copper ratio for the catalyst. The nitrogen selectivity is the highest when palladium and copper ratio of the catalyst approximately 1 by 1. So excess copper on catalyst surface hinder the hydrogen activation by palladium and lower the reaction rate. So excess palladium increase ammonia selectivity by producing more active hydrogen, but too much palladium hinder nitrate reduction by copper, lowering the reaction rate. So we compare the other nitrate reduction catalyst performances, and we confirm that these upcycled bimetallic catalysis show similar performances compared to the other researchers. So future study is to develop catalytic reduction membrane model using the gamma alumina ceramic hollow fiber membrane. So utilizing by water splitting, using hydrogen gas to increase uniformity hydrogen gas injection and scale up, and also process safety. To conclude my presentation today, palladium and copper were selectively absorbed on the gamma alumina due to the galvanic replacement reaction. The created copper palladium bimetallic catalysis showed similar reaction rate and selectivity for nitrate reduction compared to the other studies. The optimal palladium copper ratio for the nitrogen selectivity was found to be approximately 1 by 1, and excess copper hindered the hydrogen activation, while the palladium increased ammonia formation. So it is quite necessary to test using actual semiconductor wastewater or the other industry wastewater to confirm whether catalyst production is possible. So thank you for kind attention.
Considering time schedule, we can have one question.
Thank you. Very interesting talk. My question is, the catalyst that you made this way is, I suppose, is highly dependent on the composition of metal combination in the wastewater. And if you change the wastewater, you will get a completely different catalyst, which will change the catalytic performance, right? How do you adjust this issue?
Yeah, that's why I studied this study. We need to the copper and palladium ratio, optimize the ratio, right? So in this study, we optimize the copper and palladium ratio is 1 by 1. Actually, the industrial wastewater, there is not many palladium ions, right? So we first recover the copper ion from industrial wastewater, and then we know the optimize the ratio of the copper and palladium, and then we can just spike it into the catalytic to the catalyst, so we can optimize the performance of the catalyst. That's our strategy.
Thank you.
Okay, thank you for good presentation, Dr. Long. Let's move. Please give him a big hand.